we have Giulio del Zanna, who is visiting from the University of Cambridge, and he was born in Florence in Italy, where he obtained a master in astrophysics on EUV spectroscopy of stellar flares. After a PhD on extreme ultraviolet solar spectroscopy in the north of England, he moved to the south to continue to work on spectroscopy of the sun, from the X-rays to the infrared, producing atomic calculations and leading, since 2012, the Chianti Atomic Database Project. He's currently a research professor at the University of Cambridge, honorary professor at the University of Leicester, and a visiting SAO fellow. He was an amateur astronomer, then a builder and a farmer in Italy during his first 30 years, olive oil, I just learned, before spending the last 30 years in the UK researching how the photons are produced and what information we can obtain from them. And today he will talk about new satellite lines in the X-rays. I'm very happy to have you here, and please take it away.
Thank you. It's a great pleasure to be back here. I used to come here every year. I have collaborations with some of the people in the room. Because of COVID, and then my wife has been having serious health problems. I haven't been able to come here for 3 years, but now I'm back. And the reason why I'm here is, come on. Now moving. Oh, he's moving, but I'm moving here on the screen. Sorry. The reason why I'm here is that Amy is in the room, spent ages cleaning up, and the electron beam ion trap, which is in the lab in the other building, and it works beautifully. We managed to get, we put together, a team. And some of the people in the room, the X-ray group, are part of the team, and we put in a proposal. We managed to get a NASA grant for 3 years to do laboratory spectroscopy, which is really exciting. And the day I arrived 2 weeks ago, we had the first light, and I brought a champagne bottle, and we're really happy. And the whole plan is to survey the spectrum from the X-rays to the extreme ultraviolet, which is around here, and this is the region. This is a spectrum obtained from an older Chianti version of the atomic database of iron lines at 8 million degrees. So these are the flare lines from iron, and these wavelengths are the target of new important missions. This is news. The MaGIXS mission is going to be launched in 27. ECHO, Kathy Reeves here is the PI of this small explorer. It's been going through the phase 8. And there is a whole host also other new missions. UDST is also Japanese, but with contributions, hopefully it will stay from NASA. So these are big, huge solar missions. But I'm also interested because there is an astrophysics mission I don't have time to talk to you about, but I'm super excited about that. And this wavelength region, which I call from the soft X-rays to the UV, has been virtually unexplored. So recently, I submitted a paper. I found 20 of these flare lines that have never been seen before, some of them on in the lab. So the plan is to actually confirm these identifications with this sort of measurements. So this is following some work that I did started 20 years ago exactly. I went to UCL, the PI Institute of the best ever EUV spectrometer in space, which is the eyes. And when I joined the group, this was one of the first spectra we obtained. I realized that half of the lines, with these red arrows, even the strongest, they were not identified. And I was shocked. I said, what the hell is going on? And the atomic data for most of these lines were also wrong. So comparing the intensities with the calculated ones, they were off by factors of 2 typically. So I spent ages, years and years, identifying the lines, going through this theta beam spectra from Brian Fawcett. This guy single-handed identified all the strongest lines in the stream of power. He spent 30 years of his life, and he gave me, before he died, all the plates in the spectra, which I have. And I used them to identify some of these lines. Then I joined an atomic physics network of people. Then I started to do the calculations, and I calculated all the atomic data. I solved the problem in the UV. And I had to do the same thing in the soft X-rays. So it's in blue is what we have in the database before I actually did these calculations that I put into Chianti version 8, which is the red spectrum. This is in the soft X-rays, which is the target of these new missions. And in black is the quiet solar spectrum. And you can see if you compare the black and the red, it's still messy. Some lines are not in the right wavelength places. And there is a lot of still missing lines, despite the fact that I spent 2 or 3 years working on it. So now to the core of the talk. This is about the X-rays. So in 21, there was a sounding rocket that observed for the first time the sun doing spectral imaging, and a sort of producing an overlap program in the X-rays between 5 angstroms and 25 angstroms. And one of the aims of this instrument was to observe chemical abundances, measure temperature, time-dependent ionization, all sorts of things. The instrument didn't work as well as we hoped, but so the resolution wasn't that great. But what they did, acquire this instrument, they produced a model spectrum, which is the red one here, compared it to the black observed spectrum. And these groups of lines, and the lines are now 15 angstroms. I'm sorry, I use angstroms, not EV or KV. And these are the lines here, which are observed by a crystal spectrometer. There was a talk by a student here testing crystal spectrometers with the EBIT, and we really need crystal spectrometer. They give you the best spectral resolution, the best spectra ever obtained on any astrophysical source are obtained by crystal spectrometer. This is the best ever spectrum in this sort of way. It's even better than China. Okay? And what you see here is that there is a discrepancy in the lines here around 15 angstroms. This is the resonance line from neon light carbon 17. This is the strongest transition in the whole of the X-rays in any astrophysical source. Okay? So a big problem. So they came to me, they called me and said, we have a problem. It's your problem. They told me, because I could download data in this database. They said, there is something wrong. I said, no, there is nothing wrong. They insisted, oh, there is something. I said, no, there is nothing wrong, because in 2010, I published a paper taking into account some improved scattering calculation that solved a 50 years problem. For 50 years, the intensity of these lines are always been wrong. And you can see this in these busy kind of plots. But with the new scattering calculations, which I didn't make, but I tested against various kinds of observation, I was getting very good agreement. So when there is the spread of these lines, which is the ratio of the observed intensity and the emissivity of the line as a function of temperature, when the spread is small, it means there is agreement between the observed and the theoretical intensity. And before these large-scale calculations, we had discrepancies of factors of 2, and this is, these are the strongest lines in the X-rays, right? So it's a big problem. So then I told them that's not a problem. Then I realized, no, wait a minute, because they observed something which was really cold. It was about 2 million degrees. And then I realized maybe the problem is in the satellite lines. So the satellite lines were known since the 70s. This is a paper from 76, showing some laser spectra. This is the resonance line from 1970. And all these bunch of lines, these are the satellite lines from the biooptimized states in the recombined ion, in the iron 60. Okay. Now, they tried to identify these, they failed. Some of these identification, most of them actually went to NIST, which even nowadays has all the wrong identifications. Then there are people like the Livermore group. Here there is a paper observing the same lines. They claim they observed the satellite lines for the first time. They never referenced this older paper, which is typical. Nobody referenced older papers. I don't know why. There's been other papers, of course. The good news is that before going into this, trying to solve this problem, I built a code into the database calculating the intensities of these satellite lines, which are these transitions from these organized states into these bound states. It's a bit complex situation, but it's not that complicated. You need to solve a matrix of 2 ions. When I coded this in ADL, there was the first ever kind of code that dealt with this thing properly. Now there is a similar code written by Will Barnes, who's been working with me here in these days in Python. And this was released in Chianti version 9. So what I did was very simple. I had all these codes. I looked at what we had in the database. It's my fault. I put in the database what I could find. But before showing you that, I just wanted to briefly mention, because this is X-ray people, these are the results of these codes in this funny color compared to solar spectrum. This is the helium-like ion in black from a solar flare from a crystal spectrometer from SMN in the 80s. And you can see that more or less we get pretty decent agreement, not perfect, but not too bad. And this is relevant for XRISM. Now there is a lot of interest in astrophysics. I've seen beautiful XRISM spectra now with this resolution, but still, you see for the first time these satellite lines. So there is really exciting and very interesting. Another side note I wanted to mention is the fact that we published a paper 3 years ago where we found problems like 50% discrepancies in the emissivities of the forbidden line, of the helium-like ions, also the iron line. And the data are now in Chianti, because I didn't have time to put it in Chianti, but it's on Zenodo. So if people are interested, they should get the data, or if anybody has time to help me to put the data in some sort of format. Another side note is the importance of the satellite line. So when I gave a talk to the X-ray community in the UK some years ago, I asked people to raise their hands if they knew what a satellite was. And I'm not going to do it here, but the result is that even the professors didn't know. They had no clue that there were these lines. And actually, Taren in 1933, he wrote a paper showing there were these lines close to the resonance line, and they already knew what they were saying. So it's a bit shocking that nowadays people forgot what people already knew in the 30s. But then the good news is that there are all sorts of diagnostics. This was a paper by Langevin and Kim Phillips. Know both of them very well. They're really old, but they show that you can actually measure if the electrons are non-Maxwellian by measuring the satellite lines. There's lots of papers in solar physics where people measure non-equilibrium ionization and then directly the electron temperatures using these satellite lines. And also the satellite lines, this is a visual wonderful representation. If you have a transient ionization, instead of calculating ionization equilibrium, you can see that the spectra, this is the resonance line, and these groups are all the satellite lines, it's completely different. So there are huge, wonderful diagnostics opportunity. So we need to solve these problems. So when I had a look at what I put into Chianti, it was horrible. So I took the data that were previously published by a postdoc of us. I took the best spectrum. I reproduced these in gray from this crystal spectrometer, and in black is my reproduction of what the lines intensity should be. And what I found is that almost all the lines from the satellite lines were in the wrong way. So only one line in the NIST database has the correct width. And the other problem I found is that you see here is missing a lot of flux everywhere. So this was caused by the fact that the previous calculations that we ran with this postdoc, they were not large scale. They only had a limited number of configurations. Okay. And this is really important because there are hundreds of papers that people have tried to measure the electron temperatures from the ratio of these two lines, okay, and from iron 70, and they are blended with these satellites. So, when the temperature is low enough, so you have to take into account this blending. This is a well-known problem. So at the end, what I did, I ran various calculations going up to about 10,000 states in this recombined ion. And I produced these results in black, and there is pretty good agreement now. The resonance line has some opacity effects, which is a well-known problem. Not problem, a well-known thing. This happens on the sun. But now the agreement is pretty good. But I'm not sure about some of these wavelengths, and we really need laboratory spectroscopy to actually nail down some of these wavelengths. The good news is that this is a spectrum for to try to reproduce that crystal spectrometer spectrum, but there was a really hot, relatively hot active region, so the temperatures were about 3 to 4 million degrees. while the sounding rocket was about 2 million degrees. So I should have put here, if you calculate a lower temperature, all these red satellite lines become almost as strong as these other iron 70 lines. So they become really strong, okay, which is obvious. And then by doing this, I get an increased flux in these wavelength bands by a factor of 2, which matches the observation. So it looks like the problem solved, maybe not. This is a similar kind of thing. It's just showing a different spectrum from solar maximum emission active regions. So it's a different active region spectrum attributes, and the modeling is basically the same. So. The other good thing is that the case to other states from n equals to 4 and 5 are not close to the resonance line. So I was always, when I was reading textbook, satellite lines are these lines from alphanizing states close to the resonance line, as I told you. This is not true. The alphanizing states produce wavelengths anyway, okay? And the good news is that if you look here in red, I identified lots of transitions which were observed previously, but we didn't have anything in the database. And there's tons of these, there's many millions actually lines in the X-rays, and there is a need to actually, explore these further with laboratory spectroscopy measurements. So finally, in the last couple of slides, Chianti has been very successful. We received a NASA Group Achievement Award for outstanding contributions to the scientific productivity of NASA missions and the creation of a unique valuable tool for spectroscopy scientists for the world. So that's all very nice, but I want to pay a tribute to Nigel Banner. He's been leading this network. I was part of it for 20 years. This is a table of all the elements and ions we have in the Chianti database. And the yellow, the green, and the red, these are all ions that we have calculated. Of course, in the database, we have a few other ions where we take in data from the literature, but basically 80–90% of the collisional data, but also the combination data and other stuff is coming from this network led by a single person. And everybody in the world should be thankful to the UK community who paid for grants for this guy to lead this team, because all these data are not in our database. I mean, people think that my heart is Chianti. No, I'm not Chianti. I hate Chianti. Because as an atomic data producer, Chianti killed the idea that atomic data producers can do useful things. So it's been a total failure for me as an atomic data producer to distribute an atomic database in a package that people use as a black box. The same thing happens in astrophysics, XStar, in AtomDB, everything, cloudy. There are all these databases that people are pushed to publish and rush to publish without looking into the actual atomic data issues. So this is really important to realize that the atomic data, all the databases have, all come from some sources, and unfortunately now the main source is gone because he died last September. I wrote an obituary, and I also wrote after spending 3 months a paper basically releasing all the data reprocessed, the whole database that we produced in 20 years, and also produce a database of cross sections, which I'm actually using now with Amy. Yeah, I'm finished. This is the last slide. To calculate spectra, to model the spectra from this electron beam ion trap, this is a unique database. Nobody in the world has ever produced a database of cross sections. So I did it for free for the memory of this bright guy, atomic physicist, almost the last of a generation of atomic physicists. And then if I manage to hang on, I will put more data in GitHub, and I have all sorts of ideas and things. But as I said, going back to the beginning of my talk, the key thing is that we need laboratory astrophysics to benchmark this atomic data, to identify the lines. And I'm really looking forward to work in the next year or more with the people here working on this EBIT spectra. And finally, I'm advertising a job in atomic data modeling, which is not related to this, but somehow similar. So if there is anybody that is interested in this sort of stuff, please get in touch. And generally speaking, I mean, I've been in England for 30 years. I've come across a single person interested in atomic data in 30 years. And it was my PhD student, and now a postdoc, and he's looking for a job for next year. And it's a dramatic situation. So until something changes, until some bright young people want to spend some of their lifetime learning atomic physics or something, atomic physics is basically gonna die very soon. So on this sad note, I'm finishing, and thank you very much. But I'm still hopeful because there are always young people coming up, and I've met some wonderful young people that are doing this REU, and so there is still hope, especially in this country. This is a big country, so. But in Europe, it's a bit dying. Thank you.
Yeah, hopefully with the Athena XIQ, maybe there will be some increase in atomic physics interest also.
Exactly. This is
in
the
Europe.
whole point. The funding goes to big missions, the hardware and the people and the building and ground base or space base. And then when they see problems, then they see, oh, and this has happened in 30 years. Actually, every single mission had these problems. The STO is a multi-billion, they haven't never solved the problems they had. The spectrometer from eyes in UV, I solved the problem, but just mostly by myself. There's some other people did some things, but half of the lines we didn't know. I mean, this is typical. And in the X-rays, I'm sure the XRISM is going to show, and Athena, God knows what they're going to say. Yeah.
Do we have questions? I will start. So there are radiative transfer codes that use Chianti to calculate, I don't know, the emission of stellar atmospheres. There are codes that use other databases like XStar to calculate the radiative transfer in accretion disks, like cobinaries, for example. How does this satellite line problem that you mentioned influence the output of the system?
Probably not much. It depends on the temperature. If the temperature is high enough, you don't have to worry. But if the temperature is low enough, this problem was never seen because nobody ever saw a low temperature emission from the sun in the X-rays. Everybody was after the hot, bright flares and hot emission, 10 million, 6 million degrees. It was only by chance, by mistake, almost. They pointed at something, there was much lower temperature, and then boom, you have all of this. And this is typical in astrophysics. By chance, sometimes you see something. So I don't expect to be a big problem. I was talking with Adam Foster. He's been putting satellite lines for helium-like ions in his database for XRISM. And I asked, is this really important? He said, well, not much. So the sources people typically see, people typically see, there are really high temperatures, and therefore these satellites are almost in the noise in the pseudo-continuum. So they're not something to be worried too much. Well, right? Am I right, Adam? As I put a sort of right picture kind of thing?
Yeah.
Yes.
Just as a quick follow, what kind of threshold for temperature are we talking about? I mean, what are you calling high and what are you calling low?
Well, it depends on the ion balance. In ionization equilibrium, which is normally assumed on the sun and also in astrophysics, 2 million degrees threshold. At 2 million degrees, you have a lot of emission from the sodium light, iron 16, and not have that much in the neolite, iron 17. If you have 3 or more, 1 million degrees, then there is more charged state, higher charged state, and less of that. And that is reflected on the fact that all the lines, including the lines from the ionizing states, are weaker. It's as simple as that. But if the plasma is out of equilibrium, that's the beauty about these things. If we identify for sure all these lines, and then we could use them to actually check the ion balance, which is what people had tried in solar physics for 20 years, and they failed to get conclusive evidence. But they only looked at 10 million degree using the lines from the helium like iron. I mean, these diagnostics actually give you the possibility to measure the departures from the ionization equilibrium at these sort of much lower temperatures, which is unique. There is no other diagnostics in the whole electromagnetic spectrum I know that can do that. And in the future, I'm absolutely sure people will see non-equilibrium everywhere, like also non-Maxwellian electrons, because we started with simple assumptions, and as soon as the observations are more and more detailed, also the timescales of before we had exposures of minutes, and now we have exposures in seconds in the future missions. We're going to see all sorts of departures from equilibrium conditions. So people are going to have to start thinking about these things. Yeah.
I'm certainly guilty of using APEC and Charlie as black boxes and not having a clue.
Yeah, so everybody.
So what I wondered is, suppose I was a little more interested, how do I get into knowing which of the Chianti data I should be most trusting of, or least trusting of?
That's a good question. I was discussing this with Will Barnes, and we agreed that we're going to set up a GitHub discussion channel for the community to post these sort of questions. I get this question all the time, and I'm tired of answering emails to single people, because then it gets lost in the emails.
Is it
This
something you can
information-
load into the database?
No, our database has the references, but they're useless. For 20 years, we asked the community, if you work on an ion, I spent on iron 11, which is one of the first ions, coronal ion, I spent 2 years on a single calculation. Okay. And I published one paper. Okay. That's never reference, because everybody referencing the database. Right. That's why I stopped doing it. Why should I spend 1 year when I don't do anything? I'm reading these databases. I get 10,000 citations a year or something without doing anything. But no, this is the reality. And Gary Feldman is my friend in Cloudy. Cloudy is using astrophysics a lot. They have 10 times more citations than our database. Okay, he's saying the same thing. He's saying he's using the same basic atomic data, but he's having the same trouble because people don't know. People just use these black boxes, and the knowledge is sort of disappearing. So one way is to have discussions. I mean, we wrote white papers for NASA, for people at the laboratory astrophysics. Now they are closing NIST. So I mean, NIST is not perfect, but they serve the whole world with very useful. I mean, they're not perfect. Nobody's perfect. I mean, also my data, some of my indications turn out to be wrong. I mean, nobody's perfect, but we need to have an engaged discussion with the community about these things, and let the young people realizing the pros and cons of the issues. And so we're going to set up this discussion thing, which is a general thing. Hopefully it's going to be useful. We have some other ideas, but I think that's the most useful thing. And then I can post my comments like, I had a student from Japan saying, I had this XRISM data, wonderful satellite lines that we never seen. I said, well, I've seen them, in the spectra. I had them in the lab from the 80s in the sun. But, he said, I'm using Chianti. I said, oh, very good. And then he asked me, is it any good? I said, no. But that sort of information is private, right? So it should be there saying, well, you can use it, but there are limitations. And these are the limitations. So yeah, it's an issue with some what can we do?
We have time for one more quick question. There is any? Yes.
So I think I've asked Nancy this question before, but is there a sense of uncertainty, for instance, in your cross-section region, is there a sense of uncertainty to the cross-sections that you can implement? Some quantifiable things that you could say.
This is something I wanted to introduce in the database 20 years ago, because I said, first, we don't have any atomic data. Then you do the cloudy approach. And Gary Feldman cloudy approach is to put something. Could be wrong by a factor of 10, but at least it's something. Okay. That was never our approach. Our approach is only publish rates atomic data where they are published, or we calculate something that has some, reliability. Then, of course, nowadays we have multiple atomic data sets on everything. And then what do you pick and choose? I mean, I know more or less what is better, what is not. And I started to write papers comparing different calculations and looking at the structure. And that's the way to do it with some Monte Carlo forward approach. I will publish some papers, that's the way to do it. But it requires some work. But you know, in the future, this is what I would like to do. I would like to produce some uncertainties in these cross sections, which is feasible if you do these kinds of things. You know, other people, other group here in Auburn and other places, I started to do something similar. But generally, there are uncertainties which are easier. I always wanted to introduce, as I said, if I don't retire soon, I will introduce is things like the wavelength. So when we were looking at the first slide, the EBIT in CDP, the students are looking at wavelength calibration. I said, what wavelengths are you looking at? And I said, no, these are the wrong wavelengths. You have to go back to the original measurements in the 40s and the 60s. I gave them the papers where the wavelength measurements were done very accurately and they provided an uncertainty. So we generally are doing, we discovered lots of infrared lines that hadn't been observed. And now we can give an estimate on the wavelength accuracy, which is really important. So these kinds of uncertainty, because sometimes you see a spectral line or something, you don't know, maybe something else. But if you have, you know, Jenna made a big mistake thinking of identifying a line, then she had to run out and say, no, that was wrong. But this is because there was no clear idea of the uncertainty in some of these things. So if you have an uncertainty, it's really important to do these kinds of things. So hopefully we'll produce something. But you know, as I said, we need manpower. There's nobody is helping us. You know, if there's anybody, students, if you have any students or somebody wants to come and do a fellowship or something, I think try it. I'm tired. You know, I need help. Some young people, it's not what they do. But yeah, some things is coming up. I have a big grant for 5 years. I have some postdocs and hopefully some students in the future. So something is gonna come.
So it's interest rather than funding,
Yes.
interest rather than funding.
Yeah.
Oh.
That's good. The Atomic Physics Network, for several times, you advertised postdocs. We didn't have any applications. This is fully funded postdoc to work with the best atomic physicists alive. Okay? And then we tried again 1 year after, we managed to get someone who's then working in my office. I'm trying to help her to finish. This is his last postdoc from China. So normally only people from China apply to these things. So some people from China are very good, but you know, you have to spend a lot of time working with them, and there is a language barrier, things like that. But generally speaking, there's absolutely no interest in sort of stuff, which is understandable. Why should you, there are more interesting things in astrophysics.
All a matter of perspective, I would say.
Exactly.
I do like it. All right. I would say we close it with this. And so please tell your students to pay more attention to the atomic physics. All right, we will have a summer break. Enjoy the rest of the summer, the August, and we will reconvene on September 3rd. Thanks.
That's good.